I mean, would you recommend taking it? Is it useful in college?
No, it is absolutely not.
If you recommend, maybe.
Okay.
Maybe it's.
Yeah, guys, I'm gonna start the meeting. It's pretty much a recap of what we've gone over together. It's kind of summarized everything. In case you guys
Useful.
I think it's a good resource to look back on for you guys, hopefully. Because we only have one workshop left. I think someone asked on the Zoom, but also if you guys have questions, just like ask on Discord, right? If you send a message in the Discord, like one of us will be there to help you, or even just another student. I mean, 4 students too, obviously. So recap from the very beginning, we talked about what makes a good and easy AI, how you choose a data set. I think hopefully you guys have already chosen a data set. If not, then do that as soon as possible. Try to choose a data set with lots of labeled data, and there's tons of websites that have lots of data on them in these huge databases. Like Kaggle is a very common one. Also think about the data format that you're going to use, whether that's a CSV file for like data points, just like numbers in a sheet. So like a Google Sheet basically. And the other one is like obviously images is like PNGs, JPEGs, stuff like that. And if you're processing text, that might be a little bit more difficult. And think about like how are you going to process the data, right? And it needs to be labeled data. So it needs to have what is the actual correct output for each data point. And then you need to think about what your problem is. Is your problem a regression problem where it's choosing a number? Or is it a classification problem where you're choosing a class? Like in the example, it was cat, dog, or fish. Okay. Once you found your data, you want to split it into testing and training data, right? So the model learns from the training data, but it doesn't learn from the testing data. Testing data is a test to see how well your model performs. The same way your professor doesn't give you the answers to the exam beforehand. He doesn't let you basically just immediately look at the test. You just test you on it in the same way on our model. We just test our model testing data set to see how well it performs. The reason for that is to prevent overfitting. So overfitting is where the model, instead of actually learning like a general trend, like in the left image, it learns kind of each exact data point, and it just memorizes exactly which configuration it should go to. And this makes them all actually perform worse on real life data, because instead of learning, for example, in this line, instead of learning this general trend, so for points like out here, it would learn a general trend pretty well. Here, it wouldn't actually learn a general trend for points like out here, right? It couldn't learn where they are. It would probably maybe curve this way or something, right? Or even for points in this gap right here, it would be able to learn them very well. Kind of more concrete example with like, that's not just like points, is like the stop sign example that I was talking about, like where it just memorizes what a specific pixels, what the specific arrangement of pixels is that corresponds to the right class. This is a stop sign, or this isn't a stop sign, right? And you don't want to just memorize those pixels. You want to actually learn how a stop sign looks in general if you're trying to predict where a stop sign is visible or not. So once you split into training and testing data, you only train on training data. Okay, how does that data look inside of the code? It looks like a tensor, which is a complicated word for basically just saying a list of lists, or even a list of lists of lists, or a list of lists of lists of lists of lists. They can be like one-dimensional, which is the list. So let's say you have your inputs to your model, and what example we're using? I don't know. Listen, is there any good examples of like inputs to a model? Numbers. Eric. Yeah. What's a good model example?
For what?
For like inputs with numbers?
Like linear regression?
No, but like an example. What's something you can do linear regression on?
Housing prices.
Housing prices. Yeah, that's a classic one. So you're trying to, well, you predict the housing price, and your input would be like, let's say the square foot of the house. Let's say, I don't know, 10,000 square feet. It's huge. And I don't know, you have bedrooms, 2, right? Bathrooms, 4, whatever, ... So basically you have a list of numbers. This is what's called a one-dimensional tensor. It's the list of numbers. In reality, and then you have an output, which is like, okay, this house is worth, 1 million. In reality, you wouldn't just learn from this example, from this one example, right? You learn from tons and tons of examples. So you need a list of these examples. So you have a list, all right, which I'm just going to represent the list with like square brackets. where you have a list, and then inside that list you have your first example, and you have a second example, you know? Right? And then you have a second example, and you have a third example, right? And if you look at these numbers, you'll notice it kind of forms like kind of a square. It's that's what's called a two-dimensional tensor, because you basically need two numbers to select the location. You need to first choose which example you're talking about, and then you need to choose what specific item you're choosing to get a number, right? So there you have to be working with two-dimensional tensors if you're dealing with kind of numbers in and numbers out, where you have a list of them and then you go through that list. And the way PyTorch works is it often processes stuff in parallel, which is why you can input like a tensor here, which is two-dimensional, and it'll process it all in parallel at the same time. So that's kind of two-dimensional, where you have, a list of examples, and each example is a list itself. How we might think about like, okay, what if we have it's like images? Then we start to go into higher dimensions, right? So let's say we have an image here, whatever person. We have an image here, a tree. We have an image here, a cat, right? So this is a list of images. We might think of a list as one-dimensional, but really it is at minimum three-dimensional, right? Because each like pixel here, if we can imagine like kind of like taking this like each square here is like a pixel, right? Then what we get is that we can index this by a width and a height. This image itself is two-dimensional, right? We can choose a specific pixel and a specific column in a row, and then we can choose what image it is. So altogether, this whole tensor is three-dimensional. For most images, it's even actually four-dimensional, because when you choose a specific pixel here, most of the time that pixel is not one number. Most of the time that pixel is three numbers, which is R, G, and B for red, green, and blue, which is basically representing how the colors. So the colors actually come out into a fourth dimension. So for that reason, most time when you have like tensors for images, we actually have a four-dimensional tensor, where you have what image are you selecting, what column, what row, and then what color are you selecting, red, green, or blue. To actually process the files, like your .png file into a tensor like this, or a .tsv file, you can use pandas for CSV files, and you can use what's called PIL, Python Image Library, for images. And examples of that, we made a collab, which we went over previously, that kind of covers those things. And you can go through it yourself, but it has all the code there. At the bottom is images, and it starts at the beginning with CSVs. There's also data kind of cleansing here in the collab, which talks about, okay, how do you remove null values, which are like values that don't exist. You don't want those values in your data set. How do you remove unique values, which is like a value that only appears once or twice? How do you improve your class distribution? So basically, it's how often does each class show up in your data set? So for example, if you're training on, is this a picture of a cat or a dog, but you only have like 2 examples of dogs in your entire data set, that's not going to learn to classify dogs very well. So class distribution makes sure that each class that you're predicting is evenly distributed. And then rescaling data just rescales every input, but to be between 0 and 1 is kind of like a standard scaling. There's a lot more stuff you can do, which is detailed in the collab, so I'm not going to cover it super specifically. But if you have questions, those are on the slides, or you just ask me. That was kind of the data processing part. Next, we have the neural network part. The neural network, it looks complicated. You look at that image on the slide, right? There's a bunch of lines, a bunch of circles. What do they all do? What do they mean? Well, what it does essentially is each line represents a multiplication. So when you're coming in here, you have 4, 6, say 0. So these are your inputs, right? each line here means that you're multiplying it by something and then adding them together at the circle when they combine. So what do you multiply them by? You multiply them by something called a weight. And really, because you have multiple weights, you're multiplying them by multiple numbers. So here your weight might be 8. Here your weight might be -2. Here your weight might be 1. So you do 4 times 1 plus 6 times -2. That's 4 plus -12. That's like -8. And then plus 0 times 8, which is 0. So that's like -8 is the output. And then so the output sent along here would be -8. And then you just do that multiple times with multiple different weights. And these here are called like nodes. And then you could feed those outputs, like -8, into another node, or even multiple other nodes, which could then feed their own output into an output node. So from these weights, there's also bias, which is basically instead of something that you multiply this by, it's just something you add to each node. So let's say the bias here was for this specific node, there's a different bias for each one. Let's say the one here was 4. Then the results here, so -8, it would be -4. It's just like a kind of flat 4 that you always add no matter what. Or this could be negative in those cases, this thing there because you always subtract it. So with that, we can basically make the output of our perceptron or of our neural network entirely from weights and biases. And this can basically do really complicated stuff, right? Because we have all these different connections with just multiplication and addition. The issue is that multiplication isn't like complicated enough for most problems, right? We want to simulate some problem like classifying cats and dogs or something that's like more complicated than just multiplication and addition, more complicated than just linear operation. What we want is a non-linear operation. So what we do is we put a little activation function kind of at the end of each layer, right here, let's say where I'm putting a blue circle, and it's just something that's non-linear. So here's an example of something that's non-linear. It's not a straight line. What this is what's called the ReLU activation. And it's pretty simple. If it's negative, it outputs 0. Sorry, negative. And if it's positive, it keeps it the same. So 1, 2. So if it's 1, it will output 1. If it's 2, it'll output 2. If it's 3, it'll output 3. If it's 4, it'll output 4. It just keeps it exactly the same if it's positive. But if it's negative, it will output 0. So in this example, I had -4 coming out of the perceptron, coming out of this node. It's also called a perceptron. The actual output that would come after this activation, after the ReLU, would be 0. Because this activation basically makes negative numbers 0. Meanwhile, let's say in this one, inside this one, I had a number of 8, then this activation would send out 8. And basically the reason we add that is to make it more complicated, because multiplication and addition is too simple. We want something nonlinear, and we want to add something nonlinear to our model to make it solve more complicated problems. And then now we need to actually make the training loop. How do we make our model, like make predictions? Because right now we have these weights and biases, right? And the output is determined by the weights and biases, right? So we need to choose the correct weights and biases, or the correct parameters, to output correctly. For example, ChatGPT has like 3.5 billion parameters, 3.5 billion weights and biases combined. So each of those weights and biases need to be set to a number that is correct to make, good outputs, right? Like ChatGPT to like predict text. So how do we do that? That's done in a loop. And we use the data that we've collected previously, which we talked about, to learn. So the first step is we get a little bit of our data, a batch, and we make a prediction with it. So let's say we have 460, we do the forward step. And forwards takes those inputs and makes a prediction. We then do our loss. Our loss is a score of how bad our model did. So we calculate the loss. The most common way is what's called mean squared error, MSE. Mean squared error is basically you take the mean, which is the average, of the square, right? Like squaring something, like multiplying to the power of 2, of the error. And error is just the difference between the outputs and what it should actually be. So you just take the output, you compare it to what it should be, you square it, you take the average. Another one that's common is binary cross entropy. Which is used for classification problems where you're choosing different classes. Now you know how bad your model did. What the optimizer will do is to perform what's called the backwards step, which goes from the loss and tries to, how can I adjust each of these weighted biases to make that loss less bad? And it goes through and backwards and updates each of these, make it slightly better and make the loss slightly lower. And then if you just keep repeating that hundreds of times, it'll keep improving the loss until eventually you have a model that actually performs well. Lastly, for your testing loop, you want to test how well it does on kind of real life data. That's very similar, but you're not updating the weights on it because you don't want it to fit to the testing data. You just want it to kind of make predictions with the input data. You don't want it to learn and memorize the testing data. Ooh, yeah. So there was a question about if your data has specific names, should it be like a dictionary rather than a list? That should just be still a list, actually, because your neural network, it can only understand numbers, and not anything else. So if you try to put in kind of text, they won't really understand. They won't be able to do this math on it, right? You can't like multiply text. What you might have is you might have your inputs are like kind of maybe if they're like natively in a dictionary somehow. You can just convert that to a list, right? Because, for example, a dictionary really is just a list. Like, let's say you have dictionary, and then I don't know. What's the example like? In the example I had, oh yeah, for the example of the housing prices, right? Like, my thing could be dictionary, I don't know, square foot, quote, equals 10,000, right? And then that's like what each square footage is, right? But the same way you could just do with a list, you could just say list at 0 equals 1,000. So you just convert the keys like square foot to a number like 0. So it's pretty simple to convert a dictionary to a list because you just convert each key that's a string into a number. And then you need to convert it into a PyTorch tensor, but there's PyTorch can just take a list and make it into a tensor, and it'll do everything for you. Yeah. So now we have the overview of how are you doing this learning, right? You first need to initialize your model. So you decide here I have 2 layers, right? And each one had, well, yeah, let's put a third one in here, just to make it more interesting. So I had this first layer with 2 neurons in it, and I had this second layer with 3 neurons in it, right? So I need to decide that and initialize those layers. I need to initialize my activation function, which in my case I said was real. And you initialize my optimizer, which is the algorithm that kind of goes back here, and PyTorch gives you that optimizer. And you initialize your loss function, which is like mean squared error cross entropy, which PyTorch will also do for you. Then you need to write that training loop, which will make a prediction, calculate the loss, and then update the weights. And then just copy that same code basically for the testing loop, which does the same thing, but it doesn't update the weights. That's So how do we write this in code? The way I would recommend to write it is to use the class in Python. So you can make a class called like, my model or whatever you want to call it, right? And what you can do inside of normally you make a class, you just do this. But you can actually put something inside this parentheses, n, which you import from PyTorch, dot module. And this will basically tell PyTorch to, like, in the background, kind of do a bunch of stuff, give you a bunch of functions, to set up it as kind of a model for a neural network or even other stuff, but for our case, for a neural network. And we can make a constructor, which this is basically an initialization function. This is what it will do when you make it, right? And this is stuff it'll do when you make the model. So you want it to make all the layers. And to make the layers is super simple. Just say layer 1 equals n dot linear. What does n dot linear mean? It means basically one of those layers that we showed kind of in the diagram earlier. So when we had, like, let's say 2 inputs, then 3 in the layer, then 2 in the layer, then 1 output, let's say. And let's say each of these are kind of connected how they're supposed to be. Then in our case, we have 2 layers, right? One layer is here and the second layer is here. So we would make layer 1 equals n dot linear and layer 2 equals n dot linear. And additionally, we also make our activation function, which you kind of do similar. You say like activation equals whatever. I think it might be it might be a different import actually, but it's something in relive also the same way. So now later on in your code, I'm just gonna like put a kind of this bar down the screen to represent like this later on in the code. So somewhere else in the code, you can now make this model and you can say like model equals my model. Except the underscore bit. And when you call this, that means it's calling the initialization. Right? So that means that it will make these linear and really layers. So that will actually create your model. The other things you need to initialize, if you remember, is the optimizer and the loss. And that's super simple. So let's say you want your optimizer. You just say optimizer equals, I think it's like nn dot optim dot atom. And atom is one of the algorithms for the optimization that works very well. So atom, we would always recommend that you use atom. And then you want to make a loss function, which calculates your loss. And for that, you can use, I think, MSC is provided by PyTorch. I forget the exact import list. MSC is mean squared error, remember, for kind of taking the difference and then squaring it. If you're doing classification, you might do like binary cross entropy, or sorry, cross entropy loss. Yeah, so that's all the stuff you need to like initialize your model, basically. Depending on, you'd probably add more stuff here, right? If you need more layers, or if you're doing other stuff in between your layers. But now you actually want to be able to train your model, right? Because when PyTorch makes your model here, it's actually initialized randomly. So for that, use a function called forward. And in the forward function, it basically takes an input and makes a prediction. And that's super simple. You just say, you take your layer 1 or whatever layer, and then you put the input into it, like you call it with the input, and it will return an output, which is what happens to that input after going through the first layer. So then you'll have to repeat that with, repeat that with each activation and each layer. And it will basically pass it through. And at the end, you want to return the result after being passed through every single one of those. Now that you can call your function, actually make a prediction, you want to train it so that the prediction isn't just, completely random. So you need to make a loop. So I'm just going to write kind of pseudocode here, but like, for, I'm going to say for input, output in data set. So you're going to have your data set and it's going to have an input and an output. You want to first make a prediction, right? Given the input. So prediction equals my model input. So that will basically pass it through. If you do this, where you put my model, you put parentheses, and you put in the input, it will actually do some stuff in the background for PyTorch, and then call your forward function that you wrote. And then it will return whatever the prediction is based on, passing it through all those multiplications. Next, you want to get your loss. And again, you get your loss by just putting it into the loss function, which PyTorch gives you, and it basically just takes, the predicted and the actual. So predicted, and then the actual is, your output. So compare in the data set, what was the output in the data set and what was the output of your model. And you want to see how good that was with the loss function. Now you want to actually update your model. So first you want to reset your optimizer every time. So with that, I think you do optimizer dot, is this called 0_grad, which just resets the optimizer every training loop before you kind of apply a new step. Then you do loss dot backward, which is also a function, and then optimizer dot step. My handwriting is getting worse as it goes in. Four. And what this loss dot backwards will do is we'll calculate how you can adjust each of these weights, and optimizer dot step will kind of apply and update those weights for you. And if you do this on a loop repeatedly, then it will slowly improve the weights inside the model. Hopefully, you also want to be printing maybe what your loss is to see if it's doing better. Another thing you want to be doing is maybe doing a testing loop every so often, where you basically just do a prediction, just do the loss, but don't step the optimizer to see how bad your loss is on a testing set. Yeah, so that's everything for that. Kind of a review of everything. License for function. Yeah, okay, that is important. So here, when you call my model input, you can actually do my model dot forward input if you'd like. But I think PyTorch says you shouldn't do that because, I mean, honestly, I don't think it would break your model, but I think there's some callbacks it has that when you do my model without the dot forward and you just call this, what it will do is it will first actually run some PyTorch code, and then it will actually call model.forward. So if you do just my model with the input, it will actually just call model.forward. So just do it that way because there's some stuff in between that PyTorch runs to kind of, I think, handle maybe specific stuff that it's running in the background, for example. I'm not sure if it's super how important that stuff that it runs in the background is, but it's important. That's a good question though. You can Google it. I was actually Googling it earlier, like what exactly does like this do? And you can look at it. There's like some technical details. It's not really super like important to them. Yes. I was gonna say there's also an event upcoming with Jason Ishragian, who's gonna give a talk on spiking neural networks. You don't have to have any like prerequisite information to come, but he's very info. I think he knows a lot about neural networks, so I'm sure it's gonna be very informational and also very fun. I don't know, at least I think so. From the times I've seen heard him talk, which to be fair is not that often. He's very interesting. My advertisement.